at the synapse. And so our first neuron is a presynaptic neuron. Okay. Our second neuron is going to be the postsynaptic neuron. Let's just label those out. Our presynaptic neuron and our postsynaptic neuron. Okay. Now we want to start putting in our channels. So on the axon of the presynaptic neuron, we talked about the voltage-gated sodium channels. So we remember we have the myelination happening. And then at these open spots, we have lots of voltage-gated sodium channels, okay? Now, when we get to the axon terminal itself, so let's just label this area here. This is the axon terminal. And on the axon terminal, we have a different type of channel. Here we have voltage-gated calcium channels. Okay. So voltage-gated calcium channels. Right. We also want to include our neurotransmitter vesicles. So in the axon terminal itself, we have these vesicles that are in the terminal. And inside of the vesicles, we've got lots of neurotransmitter. And then let's put in some of the other players that we talked about. So the receptors, which will be on the postsynaptic side. We have a receptor that is specific to the neurotransmitter in question here. Oops. Okay, it's my little receptor. And then we have our reuptake molecule, which is on the presynaptic side. And then we have our little enzyme here, right? Our enzyme that is degrading any excess neurotransmitter. I'm actually going to put the name in here. We're going to talk about this later, but this is called acetylcholinesterase. Acetylcholinesterase. And this basically means that this enzyme can destroy or degrade acetylcholine. And acetylcholine is the most common neurotransmitter that we see at synaptic junctions. So let's start describing the steps here. So step one, we have our action potential. Oops. Right, step one is that our action potential arrives at the axon terminal. Okay. Step two is that the action potential triggers the rush of calcium into the cell. So when the action potential gets to the voltage-gated calcium channels, remember, these are voltage-gated as well. That's their mechanism. So when the depolarization of the membrane touches these calcium channels, they open up and they rush calcium into the cell. So the second step is that calcium rushes into the axon terminal. Okay. So we'll see calcium rushing in here, right? Which essentially is going to depolarize the axon terminal, right? Depolarize. Now, the third step is that depolarization triggers what's called exocytosis. So exocytosis is the release of this neurotransmitter into the synaptic cleft. So let's label this region here. This is called the synaptic cleft. Okay. And then let's look at what happens. So essentially, the neurotransmitter vesicles get really close to the membrane and they release their neurotransmitter into the membrane. So that is step 3. The release of our neurotransmitter, in this case, acetylcholine, into the cleft. All right. And now we can see all of this neurotransmitter being dumped into the synaptic cleft. Step 4, stage 4, is that the neurotransmitter binds to its receptor in question. So acetylcholine, which is our neurotransmitter, binds to, this is going to be a ligand-gated channel. Remember, we talked about this earlier. So this is going to need to have something bind to it in order to activate it. So this is kind of how we trigger that graded potential that we've been speaking about. The role of neurotransmitter is to bind to these channels, and that will essentially open them up. And so these ligand-gated channels are essentially acting in some cases as receptors as well. So they're both channels and receptors in that the binding opens them up and helps to depolarize the postsynaptic neuron. So acetylcholine binds to the receptor. Okay. And then step 4 or 5 is that we have to clear the junction. So the binding of acetylcholine to the receptor is what triggers the signal crossing, right? So we can actually put our acetylcholine here in its receptor. This is what helps the signal to be transferred. So we're starting as electrical energy, action potential, chemical energy, neurotransmitter, and then we're back to electrical energy when we depolarize by the binding of the acetylcholine to its receptor. So the signal has been sent, and now we need to clear the junction. So that would be step 5. Step 5 is to clear the junction of excess neurotransmitter. Right? Clear the cleft, synaptic cleft or junction. Okay. And so the 3 ways that we clear the junction are that we can have acetylcholinesterase essentially degrade, right? It's kind of like this little Pac-Man enzyme that degrades any extra neurotransmitter, or we can have reuptake. So on the presynaptic side, we can have the neurotransmitter be reuptaken, recycled, and repackaged into a new vesicle and essentially just kind of reuse or repurpose that extra neurotransmitter. And the third option is that it can simply diffuse away. So the third route for clearing the synaptic cleft is that it can simply diffuse away from the cleft in terms of clearing the synaptic, the cleft, right? Now, the other thing that I want to point out is that the type of response that happens on this receptor can be one of 2 types. And we're going to get into this as we move on to our 3rd and 4th learning objective here. But this can be either a fast response or a slow response. And that's going to depend on the type of receptor. So it can be a fast response or a slow response depending on the type of receptor. And we're going to move on to look more closely at what that means. All right. Okay. So essentially the steps are outlined here again. We're just going to kind of summarize them in the minutes we have left, just to kind of reiterate this. So the action potential moves down the axon, arrives at the axon terminal. These voltage-gated calcium channels open up. Calcium rushes into the axon terminal. This is going to trigger the docking of these vesicles. This is a process called exocytosis. So the dumping of the vesicles out and actually the fusing of the vesicle membrane with the cell membrane. All right. Now the neurotransmitter diffuses across the cleft, binds to its receptor. So there's a specific binding happening here. And that is what transmits the signal from one cell to the other. Now we're going to have some type of response on the cell. And this is going to vary, again, depending on the type of receptor. But the next step is that we need to clear the cleft of excess neurotransmitter in order to cease that signal. And this becomes extremely important when we talk about muscle. So if we don't clear the synaptic cleft, we end up having what's called tetanus, which is uncontrolled muscle contractions. So in order for muscle to contract, we need to send the signal, but for the muscle to relax, we need to clear the cleft. So it's really important to have the features set up to remove the excess neurotransmitter. So that can be done by degrading the enzyme or degrading the neurotransmitter by way of the enzyme. And this can be on the postsynaptic membrane, or we can have reuptake molecules on the presynaptic side that recycle the neurotransmitter into a new vesicle. All right. And then the third option is number 8 here, which is simply diffusing away from the cleft. Now, the delay between the arrival of the action potential and the signal being sent on the adjacent neuron, on the postsynaptic neuron, which is going to be a membrane potential change on the postsynaptic neuron, there's a 0.5 to 5 millisecond delay. And the reason for that is because it takes time for calcium to trigger exocytosis. So calcium needs to enter the presynaptic side and then trigger these vesicles to move close to the actual edge of the axon terminal. So that takes a lot of time. It is not due to the diffusion across the cleft. So it would kind of be, you'd kind of be tempted to think that the delay is because the neurotransmitter needs to move across the gap. And that is not so the case. It's more so because it takes time for the vesicle to get close to the edge of the membrane and then for exocytosis to happen.